Okay, welcome to Pre-Calculus, Lesson 2, Operations with Rational Functions. Now, for most of you, this class is going to be really a review from previous math classes. We're going to take a look at the various different operations. We're going to look at how to solve rational equations and check for extraneous solutions, and we'll look at solving word problems. In addition to that, we're going to look at some function compositions and impact on domain. So let's get started and give you a moment to have a go now at examples 1, pause, and then we'll go through the solutions together. Okay, welcome back. So here are the solutions. We'll take a look at example 1a first of all. The key thing when adding these rational expressions together is that we need to make sure that we get a common denominator. And the way that we do that is we multiply each expression by some form of the number 1. So in the first instance, we're going to represent the number 1 as x plus 3 over x plus 3. And in the second instance, we're going to represent it as x plus 1 over x plus 1. That allows us to get two expressions that have identical denominators, you can see here and here. And then we just simply go ahead and add the numerators together. We want to make sure that we go ahead and factor to see if there's any further simplification that can be done. In the first instance, this is not possible, but in the second example here, it is going to be possible. And I want to just take a moment to remind you of a few things to be alert to in the second example. First of all, you want to make sure that you factor. When we first factor, take a look at this expression here. If we factor out this minus out at the front, the minus here and here are going to combine together to become a plus. Please make sure that you're alert to that. Then it's essentially the same idea. We want to make sure that we get a common denominator, so we're going to multiply by the number 1, but we're just going to choose to express that in a variety of different ways. We're then going to add the numerators together, and again you see later on that there's an opportunity after some additional factoring to divide out the term x minus 1 over x minus 1, and so we're left with this final expression here. As we move to multiplying rational expressions, again, make sure that you go ahead and factor, but I'm sure most of you are going to remember how to do this. Let me give you a moment to have a go, and then we'll check in together in just a moment. Okay, so again, the key here really is making sure that you factor. I've shown way too much working here. You'll pick this up pretty quickly or remind yourselves pretty quickly, and you don't need to go into as much detail as I have here. But the first thing I've done is I've factored each expression. I've then multiplied the two fractions together, and when we do that, we simply multiply numerators and denominators. Remember, there's no need to get a common denominator in this case. Remember with multiplication that the order in which you multiply terms together doesn't matter, so I've just changed the order here, and that just helps me to see that x over 4 and x over 4 are going to divide out, and likewise x over 5 and x over 5 are going to be divided out. And then I'm simply left with this expression here. Have a go at the next one, and then again we'll take a look and work through it together. Alright, so really the purpose of this example here is just more practice and reminding you of factoring here. This expression here needs to be factored using factoring by grouping. So here's this here, and we just feeded it underneath. And then this expression here, it's really a difference of squares that's been disguised. So we're going to factor it as follows. And then x squared minus 1 can factor further into x minus 1, x plus 1. Then it's just a case of multiplying numerators together, multiplying denominators together, and looking for where we can divide out equivalent terms. And so that's all color-coded here. And you should end up with something as simple as the number 8. With division, again, I'm sure you remember, but let's pause for a moment, have a go, and then we'll check our answers together. Okay, welcome back. So the only real thing that you need to remember with division is to, again, first factor. But instead of dividing, what we do is we change the division sign to a multiplication, and then we multiply by the reciprocal of the expression. So notice how we've swapped. This numerator now has become the denominator and vice versa. Then it's just a case of multiplying numerators together and denominators together and simplifying wherever possible. Perhaps this is the area that's going to be the biggest cause for concern. How do we simplify a complex fraction? To be honest, we've looked at that quite a lot earlier on in the course, but as we move to evaluating limits later on in the unit, this is going to be really quite useful. So let me pause, give you a moment to have a go. You may use a different technique to me, but we can check our answer together on the following page. Okay, welcome back. So the first thing that you're going to do again, surprise, surprise, is factor. And once you've factored, each individual expression can be written as a mini fraction. And what we're going to do is we're going to look at just the denominators of those mini fractions. So the denominator here is 3 into x plus 2. The denominator here is 1, and then we have x plus 2. And we're going to look for the lowest common multiple of those three denominators. In this case, that's simply 3 into x plus 2. We're then going to multiply by the number 1, but we're choosing to represent the number 1 as 3 into x plus 2 divided by 3 into x plus 2. And what that does is that allows us to eliminate these denominators. So when we multiply across, you'll see that this 3x plus 2 is going to cancel with this 3x plus 2. Similarly, this x plus 2 is going to cancel here, and then we're left with this expression. We tidy things up. And of course, if we can factor and simplify, we will. In this case, we can't. All right, let me give you a moment now to have a go at this next example. And again, we'll check our solutions together on the following page. All right, welcome back. So as we look to this next example, it's already in fractional form, and the lowest common multiple of the denominators in this case is simply x squared. And once you've identified that, it's just the same process. When we go ahead and actually distribute that across and cancel, we end up with this quadratic expression over a quadratic expression. Both of them factor, and there's actually a common factor here, x minus 5. What I'd like you to start to be mindful of is the type of discontinuity this is going to represent. And an example later on will really target that. All of you have performed function compositions in your previous math classes. What we haven't really probably done is paid too much attention to the domain. So really the way a function composition works, g of f of x is really saying the function f of x plugged into g. And so we really have to make sure that we respect the domain of the first function, which in this case is f of x. You'll see that there are some other subtleties to pay attention to, but that's best explained through an example. And here is that example. So if we have the following functions, f of x and g of x, the first thing we want to do is, if we're trying to find f of g of x, is perform the composition. We then generate this complex fraction. So just as before, we're going to identify the lowest common multiple of the denominators, which happens to be x in this case. We'll multiply the top and the bottom by x. We'll simplify and factor and reduce down as much as possible. I've come up with an answer here, 2 over 2 minus x. It's perfectly okay if you came up with the answer negative 2 divided by x minus 2. Those are both mathematically equivalent. And so what is the domain of this function? Well, if you were to just look at this simplified version, it's very easy to sort of identify that x cannot be equal to 2. We also need to be mindful of the fact that, look, the number 0 cannot be plugged into g of x. So if the number 0 makes g of x undefined, we can't then go ahead and plug in an undefined number into f. So we're restricted. Not only can x not equal 2, that we saw from here, x cannot equal to 0 because that is the domain of g of x. When we're going ahead and we're starting to make predictions about the location and type of discontinuities in the graph of f of g of x, well, this here looks like quite a simple rational function. If we were to identify the discontinuity by paying attention to this denominator, I'm sure we'd all come up with x equals 2 as a vertical asymptote, just been sliced off there. So what's going on at x equals 0? Well, hopefully from the previous homework and the previous lesson, you've realized that when we have a cancelling factor, we have something called a removable discontinuity, which is sometimes referred to as a hole. And so x equals 0, there's going to be a hole. In the last lesson, we actually asked you to go ahead and find the coordinates of that hole. And the way that you would find the coordinates of the hole is you take 0 and you plug it into this simplified version. So its corresponding y coordinate would be 2 divided by 2 minus 0, which is really 1. So it's going to have a coordinate at x equals 0, y equals 1. Okay, how do we go about solving rational equations? I'm going to pause here for a second and let you have a moment to have a go. And then again, we'll check our answers together. All right, welcome back. So surprise, surprise, once again, we're going to identify the lowest common multiple of the denominators because we want to try and make those denominators disappear. In this case, the lowest common multiple of the denominators is x multiplied by x minus 1. And so when we multiply both sides of the equation by that expression, we end up with the following. These, x and x will cancel out to leave you with this expression here. X minus 1 over x minus 1 is going to cancel it out to leave you with just negative 2x. And over here, we don't really need to write that 1 in the denominator. We can just write it as a regular expression. After that, it's just simply a case of foiling out. You've got a degree 2 polynomial, and you all know how to go ahead and solve a degree 2 polynomial. Factoring is usually the way forward, but you might need to use the quadratic formula or complete the square in some instances. The most important thing to pay attention to is, have I generated any extra erroneous solutions, so any extraneous solutions? Notice that x equals 1 will make the original equation undefined. Just up here, if I plug in 1 into that denominator, I'm going to get 0. So we're going to get an undefined expression, and we're in a world of trouble. So in fact, only the solution x equals 6 will work. Of course, you can plug in x equals 6 and see does it balance the original equation, or you can take my word for it right now. For part B, again, it's a similar sort of affair. The first thing that you want to do is make sure that you go ahead and factor. Please pay attention to this minus sign here. So once we've factored, we can then go ahead and identify the lowest common multiple of the denominator. In this case, it's x minus 3, x minus 2. Sorry, that's a mistake. It's x minus 3, x plus 2. Excuse that error there. You can see x plus 2, x plus 2, x minus 3. Multiply both sides, and again, it's the same old, same old. And once again, pay attention to the fact that x equals 3 is going to make this denominator undefined and this denominator undefined. So it's an extraneous solution, and only x equals 4 works. So how do we start to deal with word problems? Well, I'm going to pause here and ask you to have a go at this one yourselves or in groups, and then we'll check in together to find out. Okay, welcome back. So the first thing we need to do is actually identify our target quantity. In this case, we want to let x be our speed from A to B. We remember from the previous unit that speed is distance divided by time, and so time has to be distance divided by speed. Then my advice to you is set up a word equation that makes sense. The total time has to be the time from A to B plus the time from to B to A. We know that that total time is 5. The amount of time it takes to get from A to B, well, that's going to be 6 divided by the speed from A to B. And if we know that the speed on the return journey is 1 mile per hour faster, that's really x plus 1. So 6 over x plus 1 is the time from B to A. Then it's really just the same case as solving those previous rational expressions. Multiply both sides by the lowest common multiple of the denominator. The one thing I will say is when you come to your final answers, check that they make sense in the context of the problem. This factor here is going to generate x equals negative 3 over 5, and of course, a speed can't be negative. You can pause if you want to have a go at the next example, but I'm really going to go ahead and dive into the solution now. Again, we need to identify the target quantity. In this case, we need to know how long will it actually take Rachel to do the job on her own. So that's what I'm going to let x be. We write a sensible word equation. The combined work rate has to be Erica's work rate plus Rachel's work rate. We know that together they can do one job per 3 hours, so 1 over 3. Erica on her own can do the one job in 5 hours. And Rachel can do one job in x hours, so 1 over x. Again, once we've established that, it's the same old mechanics to establish the value of x. In this case, it's going to be 7.5. Again, pause and have a go at the next example yourself. I'm going to dive straight in. In this case, we want to find the number of girls that actually end up going on the trip. We know that the previous per person price was reduced by $6 if 3 extra girls went. So I'm going to call that the current per person price. The current per person price is going to be 360 divided by the number of people that actually go. We're letting that be x. The previous price is that 360 divided by the previous amount of people that were going, which is x minus 3. And so again, we establish that rational equation and we use the same techniques, making sure that once we've solved the quadratic, we check our solutions. X equals negative 12 doesn't make sense in the context of this problem because there can't be negative 12 girls going on the trip. Take a moment to collect the homework assignment and make a start. Best of luck.